Oakley dokley, you've had a chance to look at this problem. Let's see how you did. The reaction of xenon difluoride and water produces two gases, xenon and oxygen, and hydrofluoric acid. If you mix 38.3 grams of xenon difluoride and 5.0 milliliters of water, what volumes of the two gases at STP will be released? The density of water at STP is 1.0 grams per cubic centimeter. I wonder why I felt the need to put that in there. Curious. All right, well, if I'm going to determine anything about this, the first thing I need to know is which of these reactants, xenon difluoride or water, is the limiting reactant. And in order to do that, I will need a balanced equation. So let us begin there. Xenon difluoride. Xenon, Xe difluoride, F2, plus water, H2O, yields two gases, xenon and oxygen. So xenon, Xe, oxygen. Recall that oxygen is diatomic, so it is O2, and hydrofluoric acid. That is just the simple binary acid, hydrogen and fluorine. There we go. Now, if I'm balanced, we're good to go. Clearly I'm not. You can see already I have at least two fluorines here, one there, one oxygen, two oxygens, one hydrogen, two hydrogens. So let's fix this. So let's see where to begin. Where to begin. I'm going to save the oxygens to last. Okay, I'm going to start here by putting a 2 here. That will fix, I just said I'm going to take the oxygens to last, but that fixes my oxygens right there. And because doing that, I can see what's going to happen. We're going to get a 4 here. And because I have a 4 here, I now need to put a 2 there. And because xenon's all alone, I can fix that with the 2 right there. So 2 Xes, 2 xenons, 4 fluorines, 2 oxygens, 4 hydrogens. So there's my balanced equation. Now, which one of these two here is limiting? Well, it says here that I have 38.3 grams of xenon difluoride and 5 milliliters of water. So 38.3 grams and 5 milliliters. All right, so time for some stoichiometry. I will start here with xenon difluoride. So if I have 38.3 grams of xenon difluoride, I first wish to convert that to moles. So up here I'll put 1 mole of xenon difluoride. And below that, I will put the atomic mass of xenon difluoride, which is equivalent to 1 mole of xenon difluoride in grams. And the atomic mass, if you look at the periodic table, that comes out to 169.29 grams per mole of xenon difluoride. Now I'm interested in how this is going to compare to our water here. So using my balanced equation, I can now go from moles of xenon difluoride, so 2 moles of xenon difluoride, 2 moles of water, so 2 moles of H2O, and finally, I want to go from moles of H2O to grams of H2O, so moles, 1 mole H2O, and the atomic mass of water is 18.02 grams of H2O. All right, so now let's do the arithmetic. So I have 38.3, 169.29 divide 2 divided by 2, that's just a wash. So let's go over here, 18.02 times 4.07, or with 3 sig figs, 4.08 grams of H2O. So what does that tell me? That tells me that if I have 38.3 grams of xenon difluoride, that I will need 4.8 grams of water to react with all of that. Now, how much water do I actually have? Well, I have 5 milliliters. Well, what is that in grams? I need to know. Well, I add at the end of the problem that the density of water at STP is 1.0 grams per cubic centimeter. You will recall that 1 cubic centimeter is equal to 1 milliliter. That means I have 5 cubic centimeters of water. And if the density is 1 gram per cubic centimeter, that means I have 5 grams of water. I only need 4.08 grams of water, so I will clearly have some water left over. That means that H2O is in excess, which means xenon difluoride is limiting. So for all the calculations I need to do from here on, I will use the limiting reactant. So what is the next calculation I need to know? Well, what volume of the two gases at STP will be released? All right, so the two gases in question are xenon and oxygen. So back to the stoichiometry. So I'm going to find out how much xenon, what volume of xenon I will produce. So starting with my limiting reactant, I will again convert that to moles. 169.29 grams of xenon difluoride. I now want to compare xenon difluoride to xenon, and the balanced equation will let me do that. So I will put 2 moles of xenon difluoride down there and 2 moles of xenon right there. Now, I want this answer to be in volume. So, as before, with all the stoichiometry you guys do, we're not going to convert it to grams at this point. We're going to convert it to liters. So how can we do that? What's our conversion for liters? Well, it turns out, I stated in the problem that these gases are at STP. STP stands for standard temperature and pressure. And at standard temperature and pressure, the temperature, meaning 273 Kelvin, or 0 degrees Celsius, and pressure of 1 atmosphere. At that temperature and that pressure, there's something that we can say about all gases. I don't care what they are. I don't care if they're xenon or oxygen or hydrogen or chlorine, doesn't matter. Any gas at 1 atmosphere and 273 Kelvin occupies the same amount of space. And that space is 22.4 liters. More specifically, 1 mole of said gas occupies 22.4 liters. That's 1 mole of any gas. So, I then now know, since I'm at STP, that 1 mole of xenon occupies 22.4 liters of space. So 1 mole of xenon is 22.4 liters of xenon because we're at STP. So you see my units cancel out, grams gone, moles gone, liters left, which is what I want, liters of. So now there's nothing left but the arithmetic. All right, so 38.3, 169.29 divide. That's a wash, 2 divided by 2, so 22.4 times, look at 5.06, or with 3 sigs, 5.07 liters of xenon. There you go, volume of xenon. Now I'm going to do a similar calculation to find the volume of oxygen. So once again, I begin with my limiting reactant, which is xenon difluoride. And I want to convert that to moles. 1 mole xenon difluoride. It's equivalent to 169.29 grams of xenon difluoride. Now I'm going to compare xenon difluoride to oxygen. So balanced equation tells me that 2 moles of xenon difluoride is equivalent to just 1 mole of O2. 1 mole of O2. I'm interested in finding the amount of liters of oxygen I have. Well, that's where this conversion will come in handy, because I know that at STP, 1 mole of oxygen occupies 22.4 liters of oxygen. All right, let's do the math. 38.3. 169.29 divide. Now that's not a wash, 1 divided by 2, so divide by 2, and 22.4 times looks like 2.53 liters of O2. And there you have it. All right, wonderful. Well, thank you for your time and attention.